where I can prove things for infinite sets, but I don't always want to talk about divisibility. Right? I might want to prove something is true for all numbers that doesn't have anything to do with divisibility, and then I don't know how to break up the numbers in such a way that I can prove something for each set. Right? So what I just did is I broke them down into sets that were mutually exclusive and then proved the property for each set. So if I can't do that with numbers, I might need to do a more complex proof. But before we do one that doesn't have divisibility, let's do another one since even numbers are pretty easy for us to understand. But let's do a proof by induction. And I'll tell you what induction is while we do it, but show you by example because it's a little bit hard to understand without seeing an example. So let's prove that same thing we did before. Prove n squared minus n is even. But we're going to prove it by induction. Now, by induction means that what we're going to do is we're going to prove it for some number, some starting point, and then we're going to assume that, and we're going to prove, that's what we're going to do. We're going to prove a basis. So we're going to prove that n squared minus n is even for a starting value of n. And then I'm going to prove an implication. I'm going to prove that n squared minus n even logically implies that this statement for the next integer, which is n plus 1, right? So I'm going to put in n plus 1 everywhere I see an n. I'm going to prove that that is even. So I'm going to prove that implication. Now, if it's true for the starting value, and this implication is true no matter what n is, then by modus ponens, it's going to be true for all of the integers. Right? So if I proved it starting, so let's say starting value n equals 0. If I prove it for 0, then I can plug, if 0 squared minus 0 is even, then that means that 1 squared minus 1 is even, right? Just by plugging those in. And by modus ponens, since I know this side is true, I would know that is true. Because my basis will prove this, and modus ponens will give me this, since I know the implication is true. And that means that the next one's going to be true. 1 squared minus 1 is even is going to imply that 2 squared minus 2 is even. Right?
How do you know your implication is true?
My implication is true because I'm going to prove this one. Once I prove it, sorry, that goes out. Once I prove it, then it proves it for all integers. And if someone hands me an integer, I can go start from 0 and go all the way up to the number they want. And I have a proof. So I basically would start with my basis and use modus ponens and the implication that I have over and over and over again until I would get the number that they wanted. So if someone gave me 24, I would have to do 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 23. And then 24 would be the last time I use modus ponens. Okay, so what I like to think about, so we're going to do this proof in just a second, but what I like to think about for induction is you're proving to someone how to walk up some stairs. You have to do two things, right? You have to get the person to the spot marked X, right? Then you have to show them how to go from one step to the next, no matter what the step is, because you don't necessarily want to go with them up all the stairs. Right? So they have to get to the bottom step, and they have to be able to get from one step to another. Or basically, they have to get on the first step. Let's say this would be my basis. And this is called the inductive step. So in the inductive step, I assume I'm at the nth step, and I prove that I can get to the n plus first step. So that's basically like proving something in the middle. I prove them how to get to the bottom, and then this rule for going from one to the next, and that will get you as high as you need to go. Because you start at the bottom, and you would iterate using your inductive step over and over and over again. So that's how I think of induction, as going up steps. If you leave out either part, then the person is stuck somewhere. Right? If I leave out the basis, they're not even on the staircase. They can't go anywhere without that. Right? They're not even at the staircase. They don't know the address. Right? That would be like telling someone to go to the course webpage and go to the notes page on the webpage and never telling them what the course webpage was. It's completely useless, right? Or if I tell them where the home page is and there's absolutely no links on there, then they still can't get to the notes page. So you have to give both pieces of information whenever you want to do induction. And this also is going to be true when we start to talk about recursion. Recursion is a really important concept in computer science. We're going to get our introduction to that in this class. And we're also going to be using induction together with it because they work the same way. Okay, so let's try this little proof we were going to do, n squared is even, by induction. We'll have to start with a basis. So we're going to start with n equals 0. Normally we're going to prove things for positive numbers, positive integers. Because in discrete math, we're usually not talking about real numbers. We don't need to worry about someone putting in 3.1 inputs into your program. Okay, they're going to do whole inputs, and if you get part of one, you'll throw away that part. Okay, so let's start. We're going to prove n squared minus n is even for n greater than or equal to 0. This tells me what my basis value needs to be. So in an induction proof, this is what I want to see on your paper. I want you to write the word basis so I can find it. Then tell me what value you're going to use for your basis. And then this is a predicate that has a variable in it, right? I usually think of this as p of n. That's what I'm going to prove. Okay, so I need to prove p of 0, right, which is equal to 0 squared minus 0 is even. I need to prove that that statement is true. 0 squared minus 0 is 0. And so 0 is even is a true statement, and I'll check it off. If it's something you can look at and think, yes, that's true, you can check it off. The next step, remember that when we do a proof, so we remember that our next step was to show that if we know p of n, then we know p of n plus 1 is true. We have to prove that statement. Right? And whenever we do a proof, we assume that the left-hand side is true, and we show that the right-hand side is true. That's what we've been doing all semester long whenever we do proofs. So what we're going to do is we're going to assume p of n is true, so we write down n squared minus n is even. That's my given. And then we need to prove, and I want to see all of these statements written on your paper, prove p of n plus 1, and that is that n plus 1, quantity squared, minus the quantity n plus 1, is even. Sometimes I'm going to rewrite my proof statement just to make it a little easier to read. But the first time you write it, it ought to be just plugging in. Everywhere you see an n in the assumed statement, you want to put n plus 1 in the proof statement. If you notice, I didn't just add 1 to this pn. I plugged in n plus 1 in place of n. That's because p of n is a function of n. And the input, I think of functions as like the post office. You send a box, so p of n is a function, and I think of this p like the post office operating on some mail that you put in the mailbox. Whatever you put in this box or this package that you send to them, they can't do anything to the inside, but they can do whatever they want to the outside. Okay, so if I do p of n plus 1, that's like a little package, and everywhere I had an n before, so this was n squared minus n is even. Okay, everything that's done to that package, I have to do this package. So I take my n plus 1, and I have to square it. And I leave it in the package, I square it, and subtract it again. So whenever you see any function, the thing that comes in the parentheses is an input, and you can't do anything to it. And you have to do the same thing to that as was done to n in the original function definition. So p of n plus 1 is usually not equal to p of n plus 1. So I want you to be really careful about that. So let's go back to our induction, unless there's some questions about this. This is really, you have to be very careful with function notation and use it properly. Okay, our proof is here. This is really, all of these steps are very important. You need to have a basis and prove it. You need to have your assumed statement and your proof statement. If you've written all of this, you're going to get 60% of the credit for a problem in this class. So I'm emphasizing this because I'm going to go grade your paper like this. 2 points, 2 points, 2 points out of 10. If you got all of these statements and you haven't even done hardly any arithmetic yet, you've got 60% of the problem. Okay, so the idea is I want you to get the form of induction and understand why it works. It works because of modus ponens and because we have a basis and we have an induction step. So the induction step is assuming this and proving this. So we have to have all three of these things because otherwise we won't have proved this and we won't be able to use modus ponens if we don't have a basis. Okay, so we have to have all of those steps. So let's now do this proof. I'm going to scooch this up.
Can you repeat where that P of n plus 1 comes from? Or that P parentheses n plus 1?
Well, in the problem definition, P of n is the statement that n squared minus n is even. That's a predicate that has a variable n. So P of n plus 1 is the very same statement, except for wherever I have an n, I have to plug in n plus 1.
Right, but where does that come from?
It comes from my problem definition right here. And this comes from that I have to prove this statement for induction to work.
Okay,
That's the definition of induction. Right, that was the step jumping thing. So I have to prove P of n logically implies P of n plus 1. Because that's the same as saying an if-then statement, right? So let's go back to our stair-stepping picture. I should have put P's on here. I really have to say that the predicate I'm proving for n is true at the nth step, and the predicate that I'm proving is also true at the very next step. Okay, so this would be some P of some n0. It might be a different starting point for different statements. So it might not always start at 0, although that's a nice, easy starting point for most things. Because algebra with 0 is very easy.
If you were doing an odd, if you were doing like divisible by 3, would you start at 1?
If I was doing what?
Like divisible by 3, like it was odd?
I can still start at 0.
Yeah.
It doesn't matter. Okay, so for this one, I need to now prove that n squared plus 1 squared minus n plus 1 is even. So let's write this in terms of, so this is P of n plus 1. I know that, just to remind you, I know from my assumption that n squared minus n is even. So if I can pull that out of this sum, then I'll know that part of it is even. And I'm hoping that the rest of it will have a 2. Okay? Because 2's tell me that we have even numbers. So if I have a sum of this plus some 2, some product with 2 and something else, then I'll know I have an even number. So I'm going to write, sorry, I put a squared in the wrong place. That was n plus 1 quantity squared. So that's n squared plus 2n plus 1 minus n minus 1 is equal to the statement I'm trying to prove, is even. I can get an n squared and a minus n, and let's group all those up at the front. So that's equal to n squared minus n plus 2n, and the plus 1 and minus 1 cancel. So I have 3 terms, 1, 2, 3, 1, 2, 3, and I've moved them around. So I know, so this is equal to 2k. Let's say that n squared minus n, since it was even, it's equal to 2 times a number k plus 2n, and that's equal to 2 times k plus n. So therefore, n plus 1 squared minus n plus 1 is even. Now it's really important that I used my assumption. You're going to be doing that every time you have an induction. You're going to be looking for something that looks like P of n. N squared minus n was a term that I had in my assumption step. So it's very important, and I did a substitution for that. I used the fact that n squared minus n was even. I used that here to show that this total sum is even. So we had 2 choices with this one. We could do an arithmetic proof, or we could do a proof by induction.
Would you have to give reasons for each of those steps during a proof?
No.
Is it mostly arithmetic anyway?
It's mostly arithmetic. This was definitely arithmetic, right? In order to be able to study from your work, you might want to give reasons for every step that you did. This is by my assumption, right? I did a substitution in. Actually, this was just arithmetic again. By assumption was for the next step. So both of these first two steps were arithmetic, then by assumption for the next step. And this is for definition. So this conclusion from here is the definition of even. So you should be able to write down the reasons for every step that you do. If you can't, then you've done a magic step and you need to go back and figure out what it was.
That's that 2 times a number reason.
Right, because even means that I can write it as a product of 2 and some other integers. And k plus n is an integer because integers are closed over addition. So I have lots of assumptions going on in these proofs that I don't need to write out because anyone who's looking at them will know that I'm talking about integers that are closed under addition. Okay, are there questions about this proof? We're done because we did a basis, we did an assume and proof statement, and then we showed that our proof statement was true using our givens. Yes?
So for induction, we only have to prove it for basically 2 cases, n and n plus 1?
We prove it for a basis, which was 0 in this case. So we have 3 things that we do.
Okay.
We prove it for a basis, then we assume that it's true for an nth step, and we have to prove that it's true for the n plus first step. So we have to prove p of n plus 1. So we really only have to prove 2 things. We have to prove p of 0 or p of whatever your start is, plus proving p of n plus 1, assuming that p of n is true. Yes?
No, you've made this look very simple. What are the real questions like?
Okay, that's what we're going to move on to next.
Second step, you should prove for basis, and then assume, right?
We assume p of n is true. So we'll put back the first slide so you can review. We assume p of n is true. We show that p of n plus 1 is true. And I want all of these statements written out. I don't want you to write just assume p of n. I want you to write what p of n is. And I don't want you to write just p of n plus 1. I want you to write what p of n plus 1 is, because most of your mistakes will come by not using the correct thing that you need to prove, or by not assuming the correct thing. So I want you to write them all out so that when you're doing your work, you'll be able to look back at them. The main reason for showing this is to know when you're done. And the main reason for this is to know what you're starting with. So you need to do both of those, because we can't solve any problem without knowing where we start and where we're going. Right? That's what we always did in our proofs, for our logic proofs, right? We had givens, we had what we were proving, and to get in between, we had to use the givens. And we knew where we were going, otherwise we would just be sitting there writing things that were true but not going anywhere. Okay, and sometimes we did that. Right? And proof by contradiction, we have the same thing. We had some givens, we had a negation of the conclusion, and we knew where we were going. We were going to a contradiction. So in every case, we want to transform a problem into something that we know where we're starting and we know where we're going to. We may not know how to get there yet, but at least we can write down those things, and that's very important. Okay, so let's do another problem. So we're going to be doing a lot of arithmetic-looking problems, and that's important because when you're doing analysis of algorithms, you're going to need to know how to deal with summations. So I'm going to do one and then show you how it's applicable first. So I'm going to first do one and then show you why it's useful. 1 plus 2 plus ... plus n is equal to n times n plus 1 over 2 for n greater or equal to 1. So before you do a proof, a lot of times it's useful just to make a chart for yourself to verify that you think it's true. Because you don't want to do an induction proof on something that it's not true because you won't ever be able to finish, right? So you should make a table to verify to yourself that this is true, because Tiffany can make mistakes. Okay? So let's make a table of n and our function. What's this ... thing mean?
Between.
It means continue in the same pattern as you were doing, which means I'm going up by 1 every time. And so how many terms are in the sum?
And
N terms, right? So here, if n equals 1, I have one term in the sum, and it's just 1. If n equals 2, it's 1 plus 2, which equals 3. If it's 3, it's 1 plus 2 plus 3, which is 6. If it's 4, it's 1 plus 2 plus 3 plus 4, which is equal to 10. And 5 is 1 plus 2 plus 3 plus 4 plus 5, and that's 15. So let's go back and fill in the other part of the table, which would be the function that we think matches with this, n times n plus 1 all over 2. So in this case, n times n plus 1 over 2 is 1 times 2 over 2, which is 1. Right? 1 times 2 over 2 equals 1. In this case, that's 2 times 3 over 2, which is 6 over 2, which is 3. In this case, I have 3 times 4 over 2, which is 6. Looks pretty good so far. In this case, it's 4 times 5 over 2, which is equal to 10. In this case, I have 5 times 6 over 2. That's equal to 15. So I'm pretty well satisfied that Tiffany didn't give me a bogus problem. And I'm ready to solve it. This also helps me get what?
Basis.
My basis. I've already proven a basis here, right? I can just use these values for n equals 1, and I will get my basis. Okay, but it's important for you to write the word basis, n equals 1, and write it out. So we're going to do that next. Anytime you have a problem like this, though, it's good to write out